All right, we've got three functions here. This logarithm with trig stuff, this inverse hyperbolic tangent with a regular sign here, and this imaginary multiplication of a inverse tangent to this exponential with the imaginary up there. All right, what do these all have in common? I will tell you. They are all solutions to this antiderivative. Indeed. And we'll take a look at that. But before we do that, pause the video and play with it yourself. Pause. Okay, onward. Alrighty, so first, we'll take this antiderivative dx, and who deals with secants, eh? So we'll convert that into cosine. Okay, now what are we going to do with that? Well, let's just multiply cosine x over cosine x, okay, dx. And what does that give us? Something a little further here. Now we got cosine x over cosine squared x dx. Well, what is that? All right, well, let's keep moving. And that equals cosine x all over 1 minus sine squared x. And this is nice because now we've got a derivative in the numerator of something in the denominator. So let's make a substitution. We'll make u equal to sine x. So du equals cosine x dx. So now the final thing that we're kind of going to do is, let's see here, u is sine x and blah, 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 blah. So really what we end up with is 1 over 1 minus u squared du. Okay, that is something that we can handle. And there's a couple of different ways that we can do it. So let's clear that, and we'll write this up again here. 1 over 1 minus u squared, and we'll forget all the du and all that other stuff because we're just going to handle what's inside the integral here. So first of all, we're going to try this with partial fractions. Okay, now we've got it in the denominator, we've got a second degree polynomial. Okay, so we want the numerator to be a first degree polynomial, but we can make it look like one. Okay, we just multiply it by 0, the u, and then plus 1. And down here, we're going to factor that into 1 plus u times 1 minus u. Okay, and that's going to equal a all over 1 plus u plus b all over 1 minus u. Can't do this without coffee with my Batman mug. Okay. Whew. Now, let's combine the two fractions here under one roof. Okay. So we'll write this as a times this thing, 1 minus u, plus b times this thing, 1 plus u, and that's all over all that business. 1 plus u, 1 minus u, Okay, and remember that all equals this thing here, right? 0u plus 1 all over the same denominator, okay? 1 plus u, 1 minus u. Okay, which means we can just, get rid of these denominators and we have an equality right here. So let's deal with that. Let's erase a bunch of this stuff then, because really we don't need it now. Alrighty, and let's get rid of all this too. Valuable real estate. Okay, that's very cute, but we'll get rid of the arrows. And let's move this upstairs. All right, awesome. Okay, so now we're making this equivalent. Let's spread this out here. So we've got a minus au plus b plus bu equals all that. Let's write it out again. It's short. All right, and now let's gather our u's together. So we've got bu minus au, and that's got that and that covered, plus a plus b equals 0 times u plus 1. Okay, so that means there's our u. So b minus a equals 0. So b equals a. That's really messy. B equals a. Ding, that's our first thing that we know. And now we have a plus b. A plus b equals 1. Well, what two things that are identical add together to give us 1? It's going to be 1/2 plus 1/2. Now, let's clear all that. Clear, bye. Okay, so A equals B equals 1/2. Okay, now, what were we doing again? We were making a decomposed fraction. So 1 over 1 minus u squared ends up equaling well, we're going to write the 1/2 like this. 1/2, 1 plus u plus 1/2, put the 1 minus u here. Okay, beautiful. Now, this is something that we can integrate, right? Du equals this. Let's just keep them separate, plus du. All right. So then we can just add up these solutions. So what do we get with this one here? Well, this one here is going to end up being 1/2 of the log of 1 plus u. And this one is going to end up being 1/2 of the log of 1 minus u. Okay? And because of this negative sign, we're subtracting. And of course, now that we've integrated, we get plus the constant. Right. Now, we can simplify this a little bit, which we will do. Bring it all under one roof. So we get 1/2 the log of 1 plus u divided by 1 minus u, and we're taking the absolute value plus the constant, whatever it might be. Finally, let us not forget to de-substitutify this. Remember, u equals sine x. So our final form is 1/2 the log of 1 plus sine x over 1 minus sine x. Absolute value thereof plus c. And this is worthy of a box, not a square. It's a rectangle. I keep calling it a square. And that's another solution. Onward. So we have something of the form 1 over 1 plus u squared. Okay? But we want something of the form 1 over 1 minus u squared, because this is the thing that we're trying to integrate. Okay, what we're going to do is switch between a Euclidean metric which is what our regular circular functions involves, to a hyperbolic metric. And to do that, we're going to replace u with IU, and that's the thing that we're going to square. And we end up with 1 over 1. Squaring the imaginary component just gives us negative 1 u squared. So that's why we get to integrate this. So what we end up with as our antiderivative is not the inverse tangent of u, but the inverse hyperbolic tangent of u plus our constant. And then undoing the substitution, we get our final solution, which is the inverse hyperbolic tangent of sine x. Isn't that awesome? Plus c. And that is worthy of a nice special colored square. Okay, onward. Now, our next and our final is with exponentials. Okay, so we've got taking the antiderivative of secant x, theta x, and we're going to convert this secant into this exponential form. Okay, so this is just the inverse of the not the inverse, the reciprocal of the cosine. Okay. Okay, now we'll rework, just working with the integrand here, we'll rework that by multiplying. Okay. Now we're going to multiply all of this by e to the ix over e to the ix, and that's going to give us the integral of 2e to the ix all over e to the 2ix plus 1. All right, now we need to do another substitution, so we'll make u equals e to the ix, and that's gives us du being I times e to the ix dx. Alrighty, so that's, again, let's clear a bunch of this stuff. Get rid of that too. Okay. Move that over there. Okay, so using this substitution, we end up with 2 over I times the integral of 1 over u squared plus 1 du. Okay, integrating this, we end up with 2 over I times the inverse tangent of u plus our constant. Okay, now we'll revert to our x, and we end up with 2 over I times the inverse tangent of e to the I x plus c, and that's our third form, which deserves a nice special colored box. And Bob's your uncle. Isn't that pretty? Now there's other ways to do this, and there's other solutions. So let us know your favorite solution to the integral of secant dx in the comments, and as always, like, comment, share, subscribe, do a little dance, and we'll see you next time.